Bismillahirrahmanirrahim. Assalamualaikum and good day everyone. So now we are on chapter 13 entitled as Universal Gravitation. So talking about universal gravitation, of course, the law that going to be involved is Newton's law, named as Newton's law of universal gravitation. So within the Newton's law of universal gravitation, it's talking about on every particle in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. So the F, so this is actually stand for gravitation, the F involved within two particles, is going to be equivalent to a universal constant, capital G, mass of the object 1, mass of the object 2, over the distance between object 1 to object 2 from center to center. This is important. The R must be from center to center square. So this kind of force is a kind of attractive force. Alright, so it means that if you have two objects, right, these two objects going to have attractive force. Let's say this is object 1, this is object 2. So here we have F, 2 on 1, F 1 on 2, and the R must be measured from center of the object 1 to the center of the object 2. This is what we call it R12. Alright, so between these two objects there is attractive force exerted on each of them. The magnitude of the force is the same but acting on different objects. So they are attracted to each other. That is why the F here, is known as attractive force. Since it is inversely proportional to the R squared, this is this law also known as obeying inverse square law. In physics, when you have a formula or law that has 1 over R squared, we call or we know that this formula is obeying the inverse square law. Alright, and the G is deduced from experiment or observation, which is equivalent to 6.67 times 10 to the power of negative 11 Newton dot meter square over kilogram squared. Now how the value of the G is deduced is actually by sort of this kind of experiment. This is what we call it Cavendish setup or experiment, where it has a set of small sphere, brown color here, with a small m mass, tied to a light string, with a mirror attached to it, that this mirror is going to measure the angle of deflection of lights, right? So another set of sphere, capital M here, is bring close to the small sphere brown here. So what will happen, the brown sphere going to move towards the blue sphere, showing that it has attractive force based on Newton's law of universal gravitation. So the amount of the deflection, the degree of the deflection is measured and deduced. So from that we can have this kind of relationship, And finally, deduce the amount of the G. Okay, as given in previous slide. Alright. So, applying the Newton's law of universal gravitation, okay, as I show you just now, if we have two objects, okay, these two objects going to experience having mass m1 and m2, these two objects going to experience attractive force, okay, towards each other. This amount of the force is the same in terms of magnitude, right? But it is opposite in direction, okay, and acting on different object, right? So basically we are going to use F12 is equivalent to, okay, negative. Why is it negative? Because of the direction. Okay, we are putting F12 as negative in direction and F21 as positive in direction. Okay, capital G, M1, M2 over R between them from center to center squared. If the particle is very small, okay, then we can directly take the distance between the objects or particle. But if we're talking about Earth and Sun or Earth and the Moon, then we have to take it center to center. Alright? Where the R must be between 1 and 2. Okay. So, okay, in terms of magnitude of the force due to the gravitation of the Earth, okay, so it's capital G, mass of the Earth, mass of the object, over the radius of the Earth square. This is when we talk about an object on the surface of the Earth. And the unit for this is Newton. Right, example 13.1. Billiards anyone? Right. There 0.3 kilogram billiard balls are placed on a table at the corner of a right triangle as shown. Okay. The sides of the triangle are of length A equivalent to 0.4, B equivalent to 0.3 meter and C 0.5 meter. Calculate the gravitational force vector, okay, on the cue ball designated M1 resulting from the other two balls, okay, as well as the magnitude and direction of this force. Alright, by make use of F21 equivalent to capital G M2 M1 over the distance between 1 and 2, which is A, okay, A squared, okay, and then after that, substitute the rest of the information or value given to us, then we will know this is the amount of F21. We are going to repeat the same method for F31. But now, the distance between M3 and M1 is actually B. So we are going to use capital G M3 M1 over B squared. So we will have this value as our F31. Alright. Then, to know the F acting on object 1 is actually a combination, right? Combination of F31 and also F21. So, we will have 6.67I plus 3.75J times 10 to the power of negative 11 Newton as the F resultant acting on the cue ball or M1. To know the magnitude of it, the magnitude of the F resultant just now, okay, we are going to use Pythagoras, okay, which give us this is the amount of the magnitude for the resultant force acting on M1. And the direction of it or angle of it is tangent theta is equivalent to Fy over Fx. okay, where we are going to have theta is equivalent to 29.4 degree. Okay, let's move to free fall acceleration and the gravitational force. So talking about, okay, object on the surface of the earth, okay, so we are going to have Fg equivalent to capital G, m of the earth, m of the object, over radius of the earth squared. And the one that we already know previously is mg. So means that the F here is also equivalent to the Fg, right? Okay, so we can cancel out the m here. We are left with, okay, gravitational acceleration or free fall acceleration on the surface of the earth. The G is equivalent to capital G, mass of the earth, over the radius of the earth squared. Okay, so this is the one that we get 9.8. Okay, where the altitude is 0 means that the height above the earth's surface, okay, from the sea level. So if it is no height, okay, exactly on the earth of exactly on surface of earth, then the G is 9.8, which is equivalent to or product of this calculation. As we do have the altitude, for example here 1000, the height from the surface of the earth, okay, 1000 kilometer, okay, then the G will be reduced from 9.8 to 7.33. So if you see here 1000 kilometer, okay, 1000 kilometer is only not only for few meters, 10 meters, 20 meters, 100 meters, no, it's 1000 kilometers, then the G will be reduced to 7.33. Okay, up to when you have 8000 kilometer, then your G will be 1.93. So means that now our formula for the Fg, okay, the R here, you have to consider the H, the altitude. So it must be radius of the earth plus H. Why is it so? Because remember, from the equation of this, the R must be from center to center between two objects here. Okay, so now we can have a general equation of our G. Okay, the gravitational acceleration or free fall acceleration is equivalent to capital G, mass of the earth, over radius of the earth plus altitude or height, okay, from earth's surface, from sea level, okay, square of this. Example 13.2, the density of the earth. Using the known radius of the earth, and that G is 9.8 meter per second, at the earth's surface, find the average density of the earth. So we have the prior knowledge just now is the gravitational acceleration is equivalent to G, equivalent to capital G, mass of the earth over radius of the earth squared. So mass of the earth is equivalent to G R of the earth, radius of the earth squared over capital G. Right. And we know that density is equivalent to mass over volume. Okay, the mass that we get from our previous equation, okay, substitute it here. Then the volume of the earth is a formula for volume of sphere, 4/3 pi r cube. Okay, substitute everything, simplify this equation. Okay, we are going to have finally the density of the earth is 5.5 times 10 to the power of 3 kilogram per meter cube. What if you were told that a typical density of granite at the earth's surface is 2.75 times 10 to the power of 3 kilogram per meter cube? What would you conclude about the density of the material in the earth interior? So, as we know, granite is the from Earth core, right? So if this is the density of the granite, it means that, okay, the value is about half the density of that we calculated for the Earth, which is 5.5, right? Okay, so we would conclude that the inner core of the Earth has density much higher than the average value of the Earth composition. So our answer should be the inner core of the Earth has a density much higher than the average value. Why is it so? Because within the core of the Earth is not only granite, isn't it? We have lots of other metal, okay, and composition of them. So if it's the only one type of material, okay, already half of the density, overall density of the Earth, okay, how about the rest of the metal? Okay, means that, okay, we can conclude that the inner core of the Earth has a density much higher than the average value that we calculated in part A just now. Okay, analysis model, particle in a field. We call it gravitational. So as we know, okay, in our system, okay, Milky Way, we have the sun as the center of the universe, okay, and orbiting the sun are the rest of the planets, including Earth here. All right, and we know that just now the gravitational acceleration on the surface of any kind of planet, for example just now for the Earth, since we are considering object on the Earth surface, so the g experienced by the object will be Fg over m of the object. Okay, and we know that previous knowledge, Fg is equivalent to mg. Okay, so even though the object is not touching the Earth, okay, but surrounding of the Earth, okay, the field surrounding of the Earth, okay, there is a field vector points in the direction of the acceleration a particle will experience if it were placed in the field. The magnitude of the field vector at any location is the magnitude of free fall acceleration at that location based on this formula or concept. Okay, if this is for bigger picture, all right, but when it comes close to the surface of the Earth, we can visualize that the field of the Earth, okay, almost, okay, in this pattern, right, okay, almost uniform. All right, so what is the meaning of the statement before? Okay, is actually like this. Okay, the field exists, the gravitational field exists whenever we can put a test particle having m mass, okay, and experiencing acceleration or free fall direction which is downward. This is due to the Fg experienced by the object, which is equivalent to m of the object times with the g of this area. This is known as weight. Example 13.3, the weight of the space station. The International Space Station operates at an altitude of 350 kilometers. An online search for the station shows that a weight of 4.11 times 10 to the power of 6 Newton measured at the Earth's surface has been lifted off the surface by various spacecraft during the construction process. What is the weight of the space station as it moves in its orbit? Okay, we know that the weight on the Earth's surface for the space station is equivalent to mg. So from here, deduce firstly the m of the space station by make use the g at the Earth's surface. So 4.19 times 10 to the power of 5 kilogram of the mass for the space station. Now, next step, we need to know the G of the space station experience within its own orbit. And the formula for the G is capital G, mass of the Earth, over the R, center to center, squared. So the R, the distance between space station and the center of the Earth, must be radius of the Earth plus the altitude or the height of the space station. Everything here squared. Substitute the rest of the values. Okay, we will get the G is now 8.82 meter per second squared. Alright, so from here, make use of this G. Okay, we are going to calculate the weight of the space station within its own orbit, which is equivalent to mg orbit, which give us 3.7 times 10 to the power of 6 Newton. So this is the weight of the space station, okay, within its own orbit.